This video on continuity and differentiability is meant for Mrs. Rose's AB Calculus class. It is meant to follow along with your continuity and differentiability notes handout that you received. To start off, in order for a function to be differentiable, that is, in order for the derivative to exist at a point, then there must first be a continuous function at that point. There can't be a vertical asymptote, there can't be a hole, there can't be a jump. If a function is not continuous at a point, then it cannot be differentiable at that point. So we're going to look at a bunch of three functions and state where they're continuous and differentiable. And what I mean by differentiable means that you can take a derivative of it. So for f of x, we have a vertical asymptote at x equals -3, so the function's not continuous and not differentiable at -3. Our second function has a hole at x equals 2, a removable discontinuity. So it's continuous from -infinity to 2 and from 2 to infinity. It's differentiable on the same interval. Our third function, which looks like some kind of square root, the domain starts at -2 and it's got a square bracket because -2 is included on that interval. The function is differentiable on the same interval, but it does not include -2 because there's no left-hand side. We'll talk more about that in a few minutes. Now we're going to look at three cases where the functions are continuous but not differentiable. The first one we have is f of x equals the absolute value of x plus 1, and this is not differentiable at 0 because the limit as x approaches 0 from the left of our derivative, which equals -1, is not equal to the limit as x approaches 0 from the right of our derivative. We call this a sharp corner. For our second function, g of x, we have a continuous function for all real numbers, but g of x is not differentiable at x equals 3 because the limit as x approaches 3 from the left of our derivative is not equal to the limit as x approaches 3 from the right of our derivative. We call this a cusp. Essentially, the difference between a cusp and a corner is a corner has more of a sharp angle, or like closer to like a 90-degree angle, whereas a cusp is just weird and kind of curvy. For our third function, we have h of x equals the cube root of x plus 2, and it's continuous everywhere, but our problem is we have a vertical tangent line at x equals -2. The slope of a vertical line is 0, and I'm going to show you what I mean on our limit definition of a derivative. It's not differentiable at x equals -2 because, and then we're going to use our limit definition, multiply the numerator and denominator by the cube root of x plus 2 squared, and when you FOIL or multiply, we're going to get x plus 2 in the numerator and x plus 2 in the denominator times the cube root of x plus 2 squared, which when these two factors divide to 1, we're going to get the limit as x approaches -2 of just 1 over this cube root of x plus 2 squared, which is 1 over 0. This is undefined, so we say the slope of the tangent line is undefined, or the tangent line is vertical. So it's an important skill for you to be able to determine x values where the function is continuous but not differentiable. And on this particular function, we have a vertical tangent line, at x equals -3, and a horizontal tangent line at x equals -7. Well, first of all, this function is continuous everywhere because we don't have any asymptotes, any holes, any jumps, anything like that. But f of x is not differentiable at x equals -3 because of that vertical tangent line. The derivative or the limit as x approaches negative 3 of the definition of a derivative, is undefined, so f of x has a vertical tangent line at x equals negative 3. There's one more point on this graph that is also not differentiable. Do you see it? It's x equals negative 1. The reason why f is not differentiable at x equals 1 is that the limit as x approaches 1 from the left of the derivative does not equal the limit as x approaches 1 from the right of the derivative. This is an example of a cusp. In order for a piecewise function to be continuous and differentiable, we need to go back to our conditions of continuity that we learned in our unit on limits. So the first thing that we're going to do is figure out what the point at x equals 4 is equal to. So we're going to use the part where the function's included 4 in the domain, and we get the y value is 12. Then we're going to see if the limit exists. We're going to do this by using left and right-sided limits. The left side of 4 is the equation x squared minus 4. When you plug a 4 into that, you're going to get 16 minus 4, which is 12. Then we're going to do a right-sided limit, which we plug 4 into 5x minus 8 to get 20 minus 8, which is 12. Therefore, the limit does exist, and f is continuous at x equals 4 because the limit as x approaches 4 of g of x is equal to the actual point g of 4. Proving differentiability is pretty much the same thing. We also have to show the left and right-sided limits of the derivative, or the alternative definition of the derivative, equal the same number. So for our alternate version of the derivative, we're going to plug in x squared minus x minus g of 4 over x minus 4 and factor the numerator, cancel the like factor, and plug in 4, which is going to be the 4 plus 3 equal to 7. For the right side limit, we're going to do the 5x minus 8 function minus g of 4 and combine like terms. When we factor out the greatest common factor from the numerator, we get x minus 4 over x minus 4, which divides to 1, so our derivative is 5 from the right. Therefore, g of x is not differentiable at x equals 4 because the limit from the left of the derivative does not equal the limit from the right of the derivative. And from the example that I missed from the previous page, we can look at this function and ask ourselves the same questions. Is f differentiable at x equals negative 4 here? And is f differentiable at x equals negative 2 here? To use the alternate form of the derivative, it would be helpful if we could write an equation for the two pieces of this piecewise. From negative infinity to negative 2, we can write the piecewise negative x plus 4 squared plus 4. It's a quadratic, it's inverted, so it's negative, it's been shifted to the left 4 and up 4. So that's how I got that, from negative infinity to negative 2. And then after and equal to negative 2, we have just a line equation, 2x plus 4. So to prove if it's differentiable at x equals negative 4, we're going to do a left and right side limit at x equals negative 4. At negative 4, when you do your left-sided limit, we're going to plug in negative x plus 4 squared plus 4 minus 4, because negative 4 is going to be, positive 4 is going to be your f of negative 4 value over x plus 4. So you can expand that square and cancel your like factors. So the slope as x approaches negative 4 from the left is 0. Similarly, x approaching negative 4 from the right, same definition, same equation, is also going to be 0. Therefore, the limit as x approaches negative 4 of the derivative exists, and g prime of negative 4 is 0. X equals 2 is a different function entirely. It's definitely got a cusp, so we say the answer is no. There is the left-sided limit when we plug in negative x plus 4 squared plus 4 minus 0, the y value, over x plus 2. We can expand our x plus 4 squared, distribute the negative, and then add in the 4. From there, I'm going to factor the numerator to get to the limit as x approaches negative 2 of negative x plus 6 times x plus 2. And obviously we have a similar factor that will cancel. When you plug in negative 2 for x, your y value, or your slope value I should say, is negative 4. From the right-hand side, 2x plus 4 minus 0 over x plus 2 factors very easily, and then you divide the common factors for a slope of 2. Well, obviously g is not differentiable because the slope from the left does not equal the slope from the right. And that's it for this video. Can't wait to see you guys back in class. Come to Chem Morning if you have any questions.